Dave Sebecki was born and raised in Cleveland and started college at Bowling Green State University, majoring in creative writing. 11 years later, he walked across the graduation stage to receive a PhD in math, a strange journey indeed. After 2 years at Franklin and Marshall College in Pennsylvania, he came home to Ohio, accepting a tenure-track job at the Hamilton campus of Miami University. Dr. Sebecki has won a number of teaching awards in his career, and while maintaining an active teaching schedule, now spends an inordinate amount of time writing textbooks and course materials. He has written or co-authored either 7 or 12 textbooks, depending on how you count them, as well as a wide variety of solutions manuals and interactive CD-ROMs. He's also worked on an awful lot of digital content that accompanies his texts, including Connect, Learn Smart, and instructional videos. Dr. Sebecki says that he's in a very happy place right now. His love of teaching meshes perfectly with his childhood dream of writing. Rumor has it he's working on his first novel in the limited spare time that he has. Dr. Sebecki is also a former coordinator of the Ohio Project Next, as he believes very strongly in helping young college instructors focus on high-quality teaching as a primary career goal. He currently resides in Fairfield, Ohio, with his lovely wife, Kat, and fuzzy dogs, McLeod and Tessa. When not teaching or writing, his passions include Ohio State football, Cleveland Indians baseball, heavy metal music, travel, golf, collecting fine art, and home improvement. So it's my pleasure to introduce to you Dr. Dave Sebecki.
That intro was so nice, it almost sounds like I wrote it myself. I'm usually a projector, not a microphone person, so if I'm blasting your ears out, someone please tell me before I actually see blood running down someone's neck. I would appreciate that. First, I want to thank Don and the committee for inviting me here. This is really, really exciting for me. There are places where I'm not even sure they'll let me speak, let alone invite me to speak. So I'm very thrilled to be here. I thank you all for sharing a little bit of your Friday evening with me. I wore my Sunday best and brought a pretty girl. So let's get started. I always bring my own applause, just in case things don't go as well as I hope. So the thing I like about this title is I think Madison Avenue would love it because it's catchy and splashy and ultimately says nothing whatsoever about the product. It's like one of those commercials where you watch the commercial and go, what was that for again? So shortly we'll find out what exactly elephants, fuzzy dogs, and teaching backwards have to do with making a course engaging. Well, that's not a good start. Thought I was going to get my fake applause again. Come on, you can do it. You know we're off the top of the screen. Oh well, it shouldn't be too bad. So the question is, what is the, it's not you, it's the tech. Don't worry about it. What is the backward approach to teaching? That's of course the first question to ask. What do you mean by teaching backwards? Well, to illustrate what I mean by teaching backwards, let's talk about a traditional approach to teaching math. This is the way I learned. Typical class, what happens? Definition, theorem. Theorems are really important, right? Abstract example. Abstract example. Abstract example. Finally, application. That's the way we do things, right? Because it's comfortable and we think, well, geez, before we introduce application problems, we need to know how to do some math to solve those problems. And we also think, well, it worked for us. That's the way we learned, right? But you know what the thing is? A lot of us have an affinity for math. A lot of our students don't. So the fact that this approach worked for us doesn't necessarily mean it's the best approach for the folks that we're dealing with on a day-to-day basis. I propose an alternate approach, which I call backward. And the idea is to start with applied problems to introduce and motivate the math. And here's the tricky part. It sounds great. Oh, applied. Everybody's into applications these days. Even if it's too early to solve the problem. Okay, there's the scary part. It's difficult to start doing this because we are all so accustomed to a way of teaching that feels comfortable, where we're not out on a limb and we think everything goes in a logical order. We love that. We're mathematicians. And then along comes this idea of, what if I start to introduce problems to students that they don't know how to solve yet? They don't have the tools. They don't have the mathematics to solve these problems yet. Well, you know, that's a little bit scary. But one of the things that it leads to is a term that I'll define here. We do stuff like that, right, as intellectuals. So productive struggle, noun. The process of discovering that everyone doesn't get a trophy, everything isn't handed to you, and sometimes you need to struggle with a problem to gain some insight. Okay, there's a lot of value in that. Productive struggle is one of my favorite terms. Students give up in math. Why? Because they have not been encouraged to benefit from occasional failure. They get to the point where, and here's why I honestly think that application problems are so difficult for most students. They are accustomed to, before pencil ever hits paper, having planned out their entire strategy for solving a problem. If you ask a student to solve a linear equation where both sides need to be simplified first, I promise you, 90% of them do not think, well, first, let's just multiply out the parentheses and see what happens. What's going on up here is they're thinking, I'm going to multiply out the parentheses, and I'm going to rearrange, get all the variables on one side, and then I'm going to solve and get x by itself, and I'll be done. Then they start writing, and that's comfortable. They want to know where they're going. Then they are confronted with application problems where that doesn't typically work unless you have trained them so well that they can mimic application problems effectively, and they're afraid to take that first step. How often do we see students leave application problems blank? Does it happen because they don't care? No. It happens because they're afraid of that first step and they're afraid of looking silly because they think, well, I don't know exactly where this is going, and if I just write something down and try something and it ends up silly, then I'm going to look stupid. And they're afraid of that. We need to build in them an innate love of the idea of productive struggle. So when I talk about teaching backwards, as you'll see in many examples, what I'm talking about is introducing a topic with a problem and asking the students to talk about it among themselves. Sometimes it's a small group activity. More often it's 3 minutes in class. I'll just say, turn to the folks around you, start to think about, and you'll see the types of problems I'm talking about. Number one, what would a solution to this problem look like? I'm not saying solve this problem, because you probably don't know how yet. If you can, that's great. Then you can listen to your iPod for the rest of the class. You don't need me. But if you can't solve the problem, what would a solution look like? What would you need to do to get a solution like this? What sorts of techniques or what sorts of tools would you need to be able to solve a problem like this? The students discuss it, make a guess. Okay, there's a lot of value in that. What do you think the solution to this problem might look like? What sounds reasonable? Okay, then we'll reconvene and I'll say, ask students for suggestions. What do you think we need to solve a problem like this? And sort of lead them into the answers that I want. And I'll say, well, here's the type of math we're going to do today, and this is the type of problem that it's able to solve. Now let's go do some math, using this problem as a framework for the teaching that I do. And then afterwards, we can go back and say, how'd you do? Try again. Now can you answer this question? And the students see this progress. They think, well, this problem that I struggled with before, sometimes it's like, wow, I had a pretty good idea of where this was headed. Other times they didn't, but they can go back at the end of the lesson and say, now I can do this. So the fact that I struggled with it at the beginning and at least got some idea of what the problem was about was productive. It was useful. So to me, that's what the backward approach is all about. And when I started doing this, honestly, it was for certain topics in certain classes, and you can't do it for every class. I mean, it's really, really difficult to do the backward approach for the product rule for differentiation. It's extremely difficult to start with an applied problem that leads to the product rule. I guess you could if you were maybe more creative than me. I'm not saying I do this every day in every class. I do it as often as I can, though. And I find that it does make a difference getting students engaged at the beginning of class. And it does give them this idea of this is not just something that a bunch of pointy-headed nerds sit around and do. There's actually some application to this. It occurred to me a few years ago that, and I maybe was going to include this later in the talk, so I could be choking already, but it occurred to me a couple of years ago that the way that we teach math to students is historically inaccurate, historically backwards, in fact, and it gives them the wrong impression. If you ask students this question, this is the truth. Students honestly believe that all math started out as abstract. There was a bunch of early pointy-headed nerds sitting around and decided one day to find x. And then 200 years later, one of them said, holy smokes, you can use this to find when 2 trains left San Francisco. Of course, we all know that's silly. We know that the math comes from applications. It all does. But they don't, because we haven't taught them that way. We teach them the abstract stuff first and then say, what can this be used for? And it sends them the wrong message. So, let's have some fun. Let's look at some fun examples, many illustrating the backward approach to teaching. First, gotta put some music. I'm gonna chorus the red dancing. So as an example of how I would use the backwards approach to introduce a topic, and as an ulterior motive to point out that many curricula, including ones that I'm trying to change at my own institution, don't really have a place for basic mathematical and scientific reasoning. We yell at students when we get them in Calc 1 and Calc 2 and they're not interested in seeing a proof of the product rule. And we wonder why. It's because we've never really told them, what does a proof mean? What is a counterexample? What does it mean to prove and disprove something? We just expect them to innately know this from high school geometry, where a proof means angle 1 equals angle 2, side, side, side. They don't get anything from that. We need to guide them in the basic idea of how you develop a hypothesis using inductive reasoning, and then how you test that and prove it using deductive reasoning. It doesn't fit in most curriculum until students get to the 200 and 300 level, and it's just a shame. So I always advocate for trying to figure out some place to squeeze this into your curriculum, and if you decide to do so. The way that I introduce this in the backward approach is through criminal investigation, which is a sort of a soft spot for me. My dad was a cop. He was head of the detective bureau, or a shift commander in Cleveland when I was in high school. And if I hadn't gone into either writing or math, I would have gone on to, I really wanted to be a profiler. I always thought that was really cool. I'm kind of like a true crime buff. So this was a pretty obvious choice for me. And I very clearly remember when the first episode of the original CSI aired. Okay, I was really excited about this because it's like, wow, there's this new show that's kind of scientific based and it's a criminal investigation show, so I'm gonna like this. And I remember watching it in 1999 with my lovely bride, and after the first episode was over, I looked at her and said, that's a really good show and it's never gonna make it. She said, well, you know, what does that mean? If you think it's really good, I said, once in a great while, the American public surprises me in a good way. They surprise me in a bad way, like 8 times a day, but once in a while they surprise me in a good way. I said, it's too smart for the general public. They are used to seeing crime fighters that drive cars fast and punch people in the neck. They're not used to seeing crime fighters that are scientists. I didn't think it was going to make it. So when it did, I said, maybe there is hope for our society after all. And so I try to use some of these things as motivation in class. Not to mention the fact that she's just really, really cute. Now I know what you're thinking, Dave. You're not with the times. She's not even on the show anymore. Well, fortunately, she's really, really cute too. There's another reason why I like this example. So, an example of the backward approach. Before starting a unit on mathematical and scientific reasoning, where I want students to learn about inductive and deductive reasoning, I will ask them this question. I'll give them some scenarios, which actually came from CSI episodes. So I went through episode guides online and I found certain scenarios. Oops, I just got an email. Oh, it's not important. Each of these is a scenario from an episode of CSI, and the idea is I will ask the students, I say, here's what we're going to do eventually. You're going to read through these scenarios, and you're going to decide which of them, in which the investigators used inductive reasoning and in which they used deductive reasoning. And of course, at first, a lot of them don't know what that is. There's the scary part of the backward approach. I'm asking them to consider these ideas, and they might not even know what the terms mean. But what I can do is ask them, which of these do you think is really good proof in court? And that's how I started thinking about this, that in a very real sense, when we hear this a lot in the media, it's like, oh, the evidence is circumstantial. When they say that, it's largely based on inductive reasoning. For example, the fourth scenario here, where the artist has sketches that match the poses of these victims, doesn't prove he was there, doesn't prove he was involved, but it certainly inductively, based on these 5 sketches, leads one to believe that he might be involved. On the other hand, the stuff that stands up as concrete proof in court, like DNA, like fingerprints, those are things that come from deductive reasoning because those are based on known principles, like the fact that if someone's DNA is left at the scene, there's about a 1 in 5 billion chance that they weren't actually there. So the students cannot tell me which is inductive and which is deductive reasoning, but they can debate among themselves which would stand up as good evidence in court, which then gives me a framework to come back later and say, remember these discussions you had about whether something really proves a person was guilty or in the room, and things that just gave you a pretty good idea that it might be true? That's exactly what we're talking about. That's what the scientific process is about. We use inductive reasoning to say, hey, this might be true, and then we use deductive reasoning to try to prove it. So it's a really good framework for beginning that. So this is what begins the unit. Then we get into the specific topic of inductive and deductive reasoning. I would be willing to bet there's at least 5 people in this room right now that have said this in front of a classroom full of students. I know I have. It's a classic, right? We use things like that. Well, if it rains, the sidewalk will be wet, but if the sidewalk's wet, it doesn't mean it rained. Okay, classics are classics sometimes for a reason, because they're simple and they make sense, but boring. Not exactly engaging. So here's something I came up with that's delightfully goofy. So my way of introducing inductive versus deductive reasoning is called fuzzy dog versus big old hole in the ground. Okay, so now we see where fuzzy dog comes from. And that is my fuzzy dog, by the way. That's Carmen McLeod. as usual, holding 2 tennis balls and saying, hey Dad, want to play? No, I don't want to leave out my other little girl, so there she is. She really loves her mom. So anyhow, here's a scenario for students. Friend calls you, has a new apartment across town, says, hey, come check out my new place, it's really cool. So you walk over, and on the way, you walk by a house with an unfenced yard. Am I getting feedback from this? You walk by a house with an unfenced yard. Dog comes running out, barking furiously, bites you on the leg. Okay, you continue on to your friend's house. You're not pleased with the outcome of that event, but it's entirely possible that the next time you're walking over there, you might take the same route. If it's the best route, you probably think it's an isolated incident. The dog got loose. Now, if you're terribly afraid of dogs, you'll never go near there again. But a lot of people would say, no, I'll probably go that way again. It's the shortest way. So let's say you do that again. You walk by the same yard, same dog comes running out, bites you on the same leg. Okay, at that point, you would probably figure out this is not the best route to take to my friend's place. In that case, you have used 2 specific, sometimes it's hard to believe I speak for a living. You have used 2 specific instances to draw a conclusion that walking this way is a bad idea. Compare that to a big old hole in the ground. If you were walking along the sidewalk and that hole was there, you probably wouldn't have to fall in the hole twice to figure out you better take an alternate path. Why? Because it is a known and proven law of physics called gravity that if you step in a hole, you're going to fall and possibly hurt yourself. There's a really, really simple and fun way to say, here's the difference between inductive and deductive reasoning. In the first case, you used specific instances to draw a conclusion. In the second case, you used a known rule without specific instances to draw a conclusion. And that's one of the silly ways that I've used teaching backwards. Next, let's talk about elephants. Suppose that one of your children comes home one day and says, Mom/Dad, I don't believe in elephants. I don't think they exist. Here's an approach you could take to address this clear problem. You could take the intellectual research-based approach. You could show them references to elephant biology and anatomy in scholarly texts. You could show them references to elephants in art, and even literature. I love this title, Jumbo, this being the true story of the greatest elephant in the world. Isn't that delightfully old-fashioned?
Hey Dave, what's the point?
Too soon.
Oh no.
So, I suggest we do this all the time in the classroom and don't even think about it. So let's go back to the scenario. Would you do this with your kid or would you do this? Take him to the zoo and show him an elephant. Wouldn't that make more sense?
Hey Dave, what's the point?
I'm glad you asked, random person in the crowd who's not a parent at all. The point is, how do we do this in the classroom? A lot of what we're trying to accomplish with the modern student is to say, math is useful. Math does get used outside the classroom. And what do we do to prove that to the students? We use application problems from the book. We use someone else's experience, and we go to the literature and say, look, here are ways that math is used. My feeling is, if you want to convince students that math is useful in their world, show them how it is useful in your world. How often have you done that? How often do you do that in the classroom? If you don't do that, if you simply rely on application problems in the textbook or in WebAssign or in MyMathLab or Connect, exactly what you're doing is the same thing as proving to your kids that elephants exist by going through the literature instead of just showing them an elephant. Think about the ways, look at your world with a childlike wonder and say, wow, here's an interesting way that I could use math in the classroom that I experienced on my own. So here's some examples of that. Topic geometry, and notice in a lot of situations the topic at the top, what I'm trying to say, I'm trying to illustrate the fact that this idea can be used in so many different areas of math. So when it comes to geometry, I call it math and home improvement, the personal touch, the idea of showing students, look, here's ways I've used math. So we're talking about geometry, there's an actual picture of my kitchen, and it kind of got cut off the bottom of the screen. I wish I knew why that was happening, but I'm very sad. This is a diagram of all the countertops in there, and several years ago we decided we wanted to replace the countertops. And we looked at 2 different styles at $56 and $75 per square foot, and we idiotically went with the cheaper one. So I can ask the students then, well, how much should we save? Okay? If they know some basic area type geometry from high school, they can answer this. It's not a trivial problem because I didn't give them exactly the measurements they need. They have to divide it up into different rectangles and do some subtraction and stuff. Excuse me, perhaps they can do that. But it's again an example of, hey, here's a way that I used geometry in my life, in my home. Now, of course, we hated those countertops. We had them for about 2 years and realized that they scratched if you gave them a dirty look. And so we went ahead and got new countertops. This time at $97.46 per square foot. So here's a great homeowner's question. How much more do we end up spending than if we had just bought the ones we wanted in the first place? So again, a nice example of using geometry in the home, but it leads into what I call an ulterior motive problem. Okay? I don't want students just to be able to find areas of rectangles and be able to find the cost of countertops. I want them to think about things that they will encounter as an adult. Hell, a lot of them are adults, right? I have a lot of, the average age in our campus is about 27. We have a lot of non-traditional students. I want them to think about the fact that using math skills and interpreting the results of them are the kinds of things that you can do to improve your lot in life, financially, employment-wise, and so forth. So that's what I call an ulterior motive problem. It just looks like, hey, here's something I've done in my home, but I also want them to start to think about issues like, oh, you know what, if I just got the right stuff at the first, I'd have done a lot better. More home improvement stuff. I apologize for how dark this is. That's the stairwell leading down to my basement. And when we finished our basement, one of the very last things that I did was this little piece of trim right here leading down. I wanted it to match up with a piece of trim that was parallel to the floor at the bottom. So what did I do? I took this piece of trim and I held it up against there and I was going to mark it off with a pencil, but it turns out those things are three-dimensional. It doesn't work so well because there's another piece of wood in the way and it doesn't match up perfectly. So, I'm thinking, oh, what am I going to do? I'll fudge it, I'll mark it with the pencil, and then I'll cut it, and it's going to be wrong, and I'm going to go back to Home Depot and get another piece. And then all of a sudden, it occurred to me, it just popped in my head, literally, these words popped into my head. Wait a minute, I'm a math professor. I ought to be able to figure this out, right? So I did. The wall wasn't painted yet, so I took a level, drew a parallel line from the top where this was, and then ended up drawing a triangle, took some measurements, figured out what the angle should be, set my saw to that angle, cut the piece of trim. And I carried it back over and I thought, well, there's no way this is going to work exactly. I'll probably have to sand it or trim it a little bit. And I put it in there and the chorus of angels sang and it fit perfectly. And I remember running upstairs going to my wife, it worked! Woo! I was so excited. It's like, wow, it actually worked. But then I thought, well, of course it worked. I'm a mathematician. That's the kind of stuff that math can do. It can give you exact answers where things actually work well. So I like giving that example to the students. This is the bar in our basement, which my wife designed on a cocktail napkin and then told me to build. And so another example of using geometry around my home is finding the dimensions of how much wood I needed to do the trim around the outside and stuff. The goal here is absolutely not for anybody to go back to their home institution and say, man, you should see the stuff that this Sebeki guy from Ohio did with geometry around his home. The idea is to just say, oh, there's some things that he did. There's ways that I use math in my life. And I want you to think about that. What's next? Probability. Pretty obvious choice. I mean, everybody uses gambling games in some way in probability, but it's not called gambling. Did you ever notice that? When you go to a casino, you don't gamble, you game. They call it gaming. That just sounds like it's less likely to cost you your house. So it never occurred to me that students were really big into gaming. I know I wasn't, because even though I shouldn't believe this, I'm a man of science. For whatever reason, I'm just not lucky at games of chance. I'm tremendously lucky in life. I'm thrilled with my life. I'm just not lucky when it comes to like rolling dice and cards and stuff. So I tend to avoid that stuff. But I was really surprised to find that a lot of college students are going to these casinos. And more areas have those popping up. I live in the Cincinnati area, and so there's there used to be casino boats along the river, but now they're actual buildings. When I found that some students were going into casinos, it was a really interesting story. I think it was a Calc 1 class. Solid C student. The kid's name was Chris. Not the kind of guy I would expect to ask me to help him solve some problems outside the classroom, sort of an independent study type thing. So he comes to my office one day, he says, hey Dr. S, I got a question for you. You know anything about craps? I say, yes I do. I know that people roll dice and yell a lot. That's the sum total of everything I know about craps. He says, well, I have a system. So I've been going to the Argosy, which is what one of the casino boats was at the time. He goes, and I was hoping that we could work together and kind of figure out the math of it and see if this actually makes sense. And this was so great for me because if he was one of the top students in class, I still would have thought it was great, but the fact that it was like a C- student who was, I think he played baseball on campus or something, I thought, well, this is fantastic. What a great opportunity. So I said, well, you're going to have to teach me a little bit about the game, but we'll work together. And we did some probability and so forth. And he was basically using, if you're familiar with the term, a martingale strategy, where he bets first. If he loses, he doubles it. If he loses, he doubles it again. And he basically decided, based on the sizes of his bets, he could afford to lose 7 straight times. And if that was it, he's done for the night. That's all he can afford to lose, and he's going to go home. And so his question was, how likely is it that I will lose 7 times in a row? So without even realizing it, he asked me a probability question. So we did the research. I talked to somebody on our statistician who knew a little bit about craps, and it turns out that he was doing it exactly wrong. There's some kind of thing where you can either bet with or against the shooter, and it did turn out that he stumbled on something that was pretty decent odds. It was maybe like 54% chance of winning on each one, and it turned out if he was going to play 7 times in a row, there was maybe a 1.4% chance of losing 7 times in a row, and it ended up being a nice learning opportunity, and I sort of forgot about it. I thought, wow, that was great. About a month later, kid comes into my office and he's looking around furtively, like Vito the loan shark is following him or something. He goes, hey, Dr. S, can I shut the door? And I'm thinking, oh my God, this kid's gonna end up in jail and it's all my fault. So he shuts the door and he goes, remember that thing we talked about last month? Yeah. He goes, well, my parents don't know I go to the casino. I've got like $2,000 in cash hidden under my mattress. So I guess probability can help in gaming. So that inspired me to use that as examples for some backwards approach in probability. And again, remember, we have not covered expected value at the time that I pose these questions to students. Instead, I say, here are the kinds of things we'll be able to absolutely, first known fact, answer shortly, but let's talk about them. So I give them a handful of gambling scenarios, and the goal is to find the expected value if you run the experiment 100 times. Very standard thing that we do in probability. And then, of course, they can't do that, because they don't even know what expected value really means at that point. But what they can do is rank the scenarios from best to worst in terms of how likely they think they're going to win money. There's one of my ulterior motives, and you'll see what I mean by that when you see the scenarios. First one, church fair, you bet $1, roll 2 dice, and here's the rules. Okay? This is an example of finding inspiration in the world around you. This literally happened. I was up, actually wasn't a church fair, that's a little bit of a fudge. It was my hometown, we call it home days. It's one of those little small town fairs, the kids look forward to all year and they spend all their quarters and come home with a fish. So me and the wife were up at this fair, and the Boy Scouts, or Cub Scouts I guess, had this little booth, and I wrote down the rules. Because I do this a lot. Once I started using the backwards approach, I started keeping a notepad on my phone and on my iPad and on my computer, and sometimes I'll just see something and there's like a little inkling, there's a math problem in there somewhere. So I wrote this down, I knew I was going to use it somewhere, and then eventually I found a spot for it. I do that a lot, like I've taken pictures of cabs. Some cabs in cities, it'll say, like right on the side, what their rate structure is, $2 for flagpole, and 1/5 of a mile is 40 cents and stuff. There's a piecewise function in there, so I see it, I take a picture, and I figure out how to use it later. There's a lot of stuff like that out there. When you start looking for it, it's really fun to look at the world that way and think, let me find some things that I can use in the classroom to jazz things up a little bit. So anyhow, that's where that scenario came from. Second one is standard American roulette. Third is a mega ball lottery with a $20 million jackpot. And fourth is the stupidest gambling game ever, where you bet $1 flipping a coin, heads you win, tails your roommate wins. So here's my ulterior motive. Which one do the students always rank worst? Flipping a coin. Because remember, they don't know about probability, they don't know about expected value. They look at it and say, well, that's stupid, you'll never win anything. Right? Because you'll win half the time, you lose half the time, and no one's ever going to win anything. Now, we, of course, as mathematicians know that's the best you're going to do in a gambling game, but they don't know that. So they almost always rank these exactly backwards. Okay, they get stars in their eyes over the $20 million, and they think flipping the coin is stupid. So then we learn about expected value, and how does it turn out? Well, the worst expected value is the lottery.
Well, duh.
Well, of course it is. That's why we call the lottery a tax on people that are bad at math. Second worst is the church fair. Okay, but it's the Boy Scouts. We'll give them their due. They can make a little bit. Third, actually, roulette's not that bad. That's about as good as you're going to do, honestly. If you do a lot of studying on probability in casinos, unless you're talking about poker where it's a 1-to-1 game, in terms of games against the house, that's probably about as good as you're going to do. I guess blackjack could be a little better if you know what you're doing. But then, of course, the expected value of 0 you can then tell the students, look, the thing that you all just instantly poo-pooed because it's stupid because you're never going to win anything, I got news for you, pal. That's about as good as you can hope to do in the long run. So then, I'm not going to preach to them and say, bad student, you should not go to the casino, because it's sort of like one of those coming of age things. They feel like, I want to do all this adult stuff now that I'm in college, and that's one of them. You just kind of want to take the opportunity to let them know, you're probably going to lose if you do these things long term. If you find it fun and you want to do that, it's fine with me. But I have a friend, one of my best friends, is a big blackjack player. I mean, this guy, I can't even watch him, honest to God. It scares me how much money he throws around and how quick it all goes. Every time he throws in, a $25 chip, I'm thinking like, dude, that's dinner out. And that's like kind of my commerce is like, well, that's dinner and that's 2 beers, and I'm not into risking that, so I can't even watch him. But he's one of these guys that gets really mad when there's someone at the table who doesn't know what they're doing because they're taking his cards. And I always tell him, look, man, the person next to you doesn't know what they're doing. They're every bit as likely to take a card that's going to screw you as they are to take one that's going to help you. Well, it never works out that way. So he always tells me, his exploits. Well, I was down 400, and the next day I lost 200. I go, let me ask you a question, money. We actually call him money, which is unrelated. I say, you go to the casino, you break even for the evening. You're pretty happy, right? He goes, yeah. I go, here's what you do. Next time you go to a casino, play the change machine. Put $1 in, it gives you back 4 quarters. Put $1 in, it gives you back 4 quarters. You play all night and break even. Oops. Okay, so we're done with probability. What does this picture have to do with teaching college mathematics? My answer is absolutely nothing. I just think it's a really, really cool picture. I stumbled across a picture of a monkey riding on a dog, and I thought there's got to be some way I can get this into my talk, and I couldn't think of a really relevant way, so I put it in anyhow. Look at the little booties. It actually says cowboy on the booties, and the monkey's got a little hat and stuff. Although one time, when I was giving this talk and I posed that question, there was one really good answer I got to the question, what does this have to do with teaching math? Somebody in the very back of the room raised his hand and said, it's non-commutative? I actually spent about 40 minutes this week trying to find a picture of a dog riding a monkey, and I couldn't find one. Thank you for indulging me in that. Statistics. It's one of my favorites about observing the world around you, math and biology. Most of us have seen either this exact picture or one an awful lot like it. We call this a living histogram. What a great idea. At some point, I believe, it's really hard to see because it's so dark, but I believe this is at the University of Connecticut because there's a really, really cheesy helmet up on the middle of the field. I think it says UConn. But someone got this great idea of measuring students, lining them up, and then taking a picture from the press box. And you can see, the normal distribution of the men and of the women, and you can talk about bimodal distributions, and it's great. There's one sad thing about this, though, because it's such a famous picture. Notice there is no sign for 4'11". There is, however, a sign for 4'10", but there's no one behind it. You know what that means? It means the 4'10" person overslept and they missed out on their opportunity for mathematical immortality. That's kind of sad. So anyhow, we look at this as mathematicians and we go, wow, that's great. What an awesome example. A student in 2014 looks at this picture and they see this. They see like a Civil War daguerreotype. It's like, oh my God, it's in black and white. Look at that cheesy helmet in the middle of the field. And you lose them just based on that. They can't see the great mathematics that's in there because it just looks so archaic and silly, and they're busy making fun of people's clothes. So I'm trying to think about, I thought that was on my slides for a second. I'm trying to think about, well, what can I do to kind of bring this idea to life? And I'm literally, this is honest to God truth, I'm sitting on the back deck at my house in a beautiful day in, I want to say, April. This is a maple tree. It's not my maple tree, but it's a maple tree. We have this big maple tree that I'm looking at in the backyard, and I'm sitting there looking up at the sky thinking, what can I do that's better than just showing that cheesy old living histogram picture? Well, if you spend any time around maple trees, you notice that they drop these things by the millions in the spring. Depending on where you live, some people call these things helicopters. Some people call them whirlybirds. If you want a swimming pool, you call them a big pain in the ass. So I'm sitting there watching these things fall on my pool cover thinking, oh, every year they make this mush when it rains and it's so hard to get them off and stuff. And all of a sudden, it was like, again, the skies opened up and there was a chorus of angels, and it occurred to me, human beings are not the only things that vary normally in size, I bet. So I sprung up from my chair and I ran down into the yard and just started scooping up these seed pods. I put them in my hat, actually, and I brought them inside and started measuring them. I counted out 100 and I measured them. Look what happened. A real living, recognize the countertops? Those are the countertops from my kitchen. So, I divide them into classes based on their lengths. There's 100 of them there. And here's what happened. When I started laying them out, the 46, 47 category, I think 4 of the first 6 were in that category, and I started to panic. I thought, oh man, this isn't gonna work. I just wasted my time counting out all these 100 seed pods, and shame on me. That in itself, when I show this to the students, give me an opportunity to tell them, to teach them a lesson about the value of not making assumptions based on a small sample. I should know better. I'm a mathematician, I swear to God. I can show you my mom has my degree, but I can email it to you. I should know better, but I didn't. I panicked. And I made myself promise that I wasn't going to fudge the results. Boy, I was tempted. I was thinking, I'm going to lay this out so it's like a beautiful living histogram. But I said, I'm not going to do that. If it doesn't work, I'm going to find a different example. And of course, it did. In the long run, with 100 seed pods, it actually worked out pretty nicely. So that's an example that I'm really, really proud of, even though the countertops are now gone. By the way, I'm just going to apologize. I'm not going to have time during my night talk later. I apologize for the fact that there's repetitiveness in my night talk because I usually give that before this talk. So, another thing from statistics that I think is really, really cool. We talk a lot about correlation, at least when I teach stats. I'm really big on correlation. I'm really big on finding regression lines and things like that. So, what's the biggest issue we have in teaching correlation and regression? That didn't sound like it, but that was a question. What do students struggle with most in correlation? Think interpretation. I should have supplied Matt an answer for this one too.
Correlation does not imply causality.
Thank you very much. Okay, students struggle like crazy with that. You know why? How do we teach correlation? We want we want these really great shiny examples of correlation. So the first 4 examples we do are things we know are going to be correlated because one causes the other. And then, afterwards, we say, well, now correlation does not really mean causality, but it's already been imprinted in their brain that, well, what does correlation mean? It means one thing causes another. So I'm not going to do that. First example I do of correlation is going to be one where we can talk about, does it make any sense that there's causality here? So I did some research online, and I found this really intriguing article on the internet titled, Does MySpace Cause Illiteracy? Or it was a connection between MySpace and illiteracy or something like that. I thought, boy, this is something I gotta read. I literally did a search for correlation, causation, and this is one of the things that came up. So it turns out, if you are a member of Google, whatever that means, if you have a Google sign-in, like a Gmail or Google+, there are places you can get to where they do a lot of correlations. Now the Google people, they're like the NSA of the West. I mean, they track everything. Every single search gets tracked somewhere. They can tell you on any given day, literally, how many people in the world search for a certain term. So all these terms, they have a search score. Now what that means is a scaled score from 0 to 100 that represents how likely it is that any given individual in a certain area searched. So in this one place, it's called state stats. They divide all these statistics up by states, and then they show you correlations. So someone just was playing around with this and putting in things that clearly should have no relationship whatsoever. And they found that one of the stronger correlations in the state stats was likelihood of searching for MySpace with percent lacking basic literacy. So on the vertical axis, we have that state or MySpace search score, which says for any given state, how likely it is that someone in that state is going to search for the term MySpace. Along the bottom, we have the percent lacking basic literacy. And that is a really strong correlation. I used to know what it is. I want to say it's like 0.7 or something. And for a sample size of 50, it's like way beyond the 1% certainty level. So the point of this article was, well, geez, then clearly there must be some causal connection between these two. So, I can show this to students, and they don't know what the R value means, but I can say, well, look how the ones that tend to be on the left are lower, and the ones that tend to be on the right are higher, which means In a state lacking basic literacy, it's more likely that people are using MySpace. So then we talk about, well, does that make any sense? Well, let's see. If you are lacking literacy, are you more likely to use MySpace? Well, no, that doesn't make any sense, because if you're lacking basic literacy, you can't read anything on MySpace. If you use MySpace, does that make you illiterate? Well, that's even sillier. Okay, is there a third variable that connects the two? Maybe there is. Maybe there's not. Maybe it's just a big coincidence. I don't know. I think it is, honestly. I think it's just a big coincidence. Or maybe there's some third variable we can't find. But there's my first example, real example of correlation, where I can sort of let students know we're not going to play that game, where if two things are related, we just automatically assume that there's a good reason for it and that one causes another. Correlation is not the end of the story, it's the beginning of the story, where we then examine further and try to decide if there's a good reason for that correlation. What's next? Ah, yes. Oh, man. Again, off the screen. Those are blinking saying public service announcement. Here's a public service announcement. We interrupt this talk. What do these problems have in common? So what I did is I went to my bookshelf, and I'm sure we all have, dozens of algebra books on our shelves, and I just grabbed 4 random books, none of which is mine, I should say, to be fair. And I found a word problem in an algebra book. Okay, so here's the first, where we're minimizing the cost of producing chairs. Next one, medical research indicates, so now we're talking about something sort of timely and relevant, the risk of having a car accident based on alcohol use. Next one even has a source, the NEA, so it's based on certain statistics, and we've got a function here which then describes something, and we're asking, we're studying then the average salary for secondary teachers. Next one, not only does it have a source, it's even got a cool graph. So now we're talking about SUV sales. Totally different topics, different books, different layout. What do they all have in common?
Modeling's already been done.
Say that again, please.
Modeling has already been done.
You win a Reese cup. The truth is, I was going to offer a choice of either a Reese cup or a Frosty adult beverage from my cooler. But then I stumbled across this in the pool today. I went for a swim this afternoon, and I found this helpful thing posted by the pool. A person is guilty of drinking alcoholic beverages in a public place when he drinks alcoholic beverages in Thanks for clearing that up. So yeah, what do those problems all have in common? The function is provided. You ever had a student literally ask that question, where do these functions come from? I used to get that a lot, and you know what my answer was? I would make a smart aleck remark. I'd say, well, I guess, that's why you make a lot of money if you get a degree in math. You can find those functions, ha ha ha. Well, now what can we say? Where do they come from? You got a graphing calculator? Can you put some data in and find a model? Public service announcement, put that in your algebra curriculum. Stop relying strictly on canned problems where the function is provided. We think they're real, we call them real, we even cite a source, but they don't look real to the layperson because this function just magically appears. When you show them where those functions come from, that they can find them from real data, it just brings it to life for them. While I'm at it, while I'm in the public service announcement, see, this time you can actually see it. This is totally off the topic, it's got nothing to do with teaching backwards, but it's my latest crusade. I have started asking my students, literally asking them by asking them to fill out answer the question on a small sheet of paper, what is variable? I've asked this from everything from beginning algebra up to Calc 2. Most common answer? I bet you can guess this. Oh, it's a letter, like X. Or something. I've actually seen a printed beginning algebra textbook. Actually, it was a Cliff Notes algebra book that defined a variable as a letter, that blah, blah, blah. And I stopped and said, I can't put this book in the hands of students. No, it's not. Variable's not a letter, it's a thing, it's a quantity that can, vary. Ask your students if they know what a variable is, and you will get a real understanding for why a lot of them don't get algebra. How can you possibly expect someone to understand algebra if they fundamentally don't know what a variable is? They think it's a letter, and then they can understand why we're doing math with letters. They don't fundamentally know, and it's not their fault. I'm not here to trash students. If students don't know what a variable is, it's not their fault. It's the people who pass them through an algebra course, even though they can't intelligently answer the question, what is a variable? When we wonder why students struggle with algebra, there's the very first reason. They fundamentally don't get the idea that a variable is a quantity. So I will do examples. I'll actually ask them to use symbols other than letters for variables to break out of that box. I'll tell them, why do we use letters? Because what are the most common symbols that everyone knows? Numbers and letters. Well, you can't use numbers because then it's not variable anymore, is it? So we use letters. We don't have to. I'll do examples where I use a smiley face or a little picture of my mom or something like that. And I want them to do that, to get the idea. How often, even in a calc class, they'll study. I did this in my calc class yesterday. We derived the formula, derivative of natural log x equals 1 over x. Monday I'm giving them a quiz on natural log formula, and one of the problems is going to be to differentiate natural log of y. I bet you a third of them, their answer is going to be 1 over x. Why? Because over the weekend they're going to stare at that formula and memorize it. Derivative of natural log is 1 over x. There's that disconnect. They don't get the fact that the actual letter doesn't matter. So take that for what it's worth. Moving on. What's next, Dave? Adding and subtracting signed numbers. This is here just to point out that the backwards idea doesn't have to be fancy stuff. It doesn't have to be probability or inductive and deductive reasoning. It can be simple stuff. This came from another in-class scenario, intermediate algebra class. I was simplifying I was doing a subtraction of polynomials on the board, I guess. And at one point you distribute the negative, and then I just kind of gloss over. Well, look, it's minus a minus, so we add that. Move on. Everybody just dutifully writes it down. Well, two students stop at the end of class. Again, not what you would call like future mathematicians. Both nice kids, solid B- students. Said, hey, Dr. S, we got a question about this one thing from class. And they showed me their notes. Remember when you did this and you said minus and minus the pluses? Yeah. He goes, well, we know that's true. We know that when you subtract a negative, you turn it into plus, but we don't know why. And I was just like thunderstruck for a second for this to happen in an intermediate algebra course. I said, guys, I got so excited. I remember going like this. I go, guys, that is a great question. You have just crossed the line that separates childhood mimicry from adult learning. You want to know why. The things that you memorize as kids, finally, you've grown to the point where you're saying, I don't want to just copy stuff down anymore. I don't want to just mimic what this guy does. I want to understand. So I used that as an example in the class the next day. I didn't want to call these guys out and embarrass them, but I did, because that's what I do. And I said, okay, everybody, here's what happened after class yesterday. And I still use this as an example in my classes. It was probably 4 years ago. I said, this is what you should be doing. This is what getting an education actually means. Questioning why. And I use Shakespeare as an example. I like to pick on literature and history people. Again, it speaks to the idea of why it's important to prove stuff. So suppose you're in an English literature class, and you're reading a passage from a Shakespearean play, and the instructor says, well, clearly what the bard was talking about there is the future rise of reality TV. Are you all just going to sit there and go, oh, no kidding, and write that down and move on? Or is someone going to raise their hand and say, wait a minute, back that up, man, that doesn't make sense? Say, in every other class, people that are getting an education are comfortable with challenging professors and saying, I don't think I'd buy that. Can you tell me why that makes sense? But in math, they just want to sit there and write stuff down. So I will tell them, and use this as an example, not only should you accept it when I prove stuff for you in class, you should freaking insist on it. So anyhow, I was so excited by this. My answer to the kids on that day, I said, you know guys, that's such a good question. Let me think about it overnight. I don't want to give you just some lame answer. I want to come up with something that's going to sort of bring it alive. This ended up in one of my textbooks. I thought it was such a good idea. So I came up with this idea of PayPal balances. And a great way to teach arithmetic with negative numbers is financial stuff, debits and credits and so forth. So the key question here is B. You've got all these different transactions. And I asked them to find the differences of the balance for Thursday and Friday. So like dutiful students, they've learned, well, the difference, you subtract the ending minus the beginning, and they do 20 minus 25, and they get 45, because by God, they know that they're supposed to add when they subtract the negative. But then the key question is, what does that tell you about the account activity? And they look at it and say, well, let's see, I was 25 bucks in the hole. Then now I have 20 bucks. Hey, I added $45 to my account, and they even use the word ding, ding, ding. And when I give it to those students, they loved it. They were so excited. They said, you know this thing that I learned in grade school and never understood? It's so easy. It makes perfect sense. So even simple little things like subtracting signed numbers, you can come up with useful everyday examples that will bring it alive for the students. Logic, one of the banes of our existence in the liberal arts math course. Students just, they go nuts over this stuff like P implies Q. Who cares? Who cares about P and Q? So math and mind control is my way of talking about the idea behind logic, how it's about being able to decide if an argument makes sense or not. So what I want them to think about is debate over the merits of arguments that are somehow opinion-based or emotional. So here's my teaching backwards. You're supposed to decide if this argument is valid, meaning the conclusion can be logically drawn from a set of statements. Now, of course, they don't know what that is at first, so I had to define that. Here's what valid means. And then eventually we'll be able to come back and you'll be able to answer these. So here's the scenarios that I give them. Start off with something really simple, non-controversial. When there's smoke, there's fire. Okay, now we'll talk about money. That's sort of a hot button issue. College football. Well, you want students to argue, talk about college football. So what I'm having them do is debate among themselves whether these arguments are valid or not. Okay, now the next couple, some of you, I get this, some of you would be boiled in oil before you would bring something like this up in a class. I completely understand, it's not for everyone. Something involving religion, something involving politics. Okay? Students get really emotional about this. Some people say, well, of course that makes sense because, that's what my church teaches me. Or they didn't think we should go to war. And they argue, and they argue, and they argue, and then I give them sort of a silly one at the end. And this is the only one that's logically valid. Okay, the rest are not. They spend a bunch of time arguing about whether these arguments make sense, and not one of them typically thinks about whether it's logically valid. It's completely based on their opinion of whether they think the conclusion is true. So before I ever show them P implies Q, P and Q, I talk about, okay, it turns out that all of these are silly arguments, and I don't care what your opinion is, they don't make any sense. And I'll pick one of them and say, here's why that's not a valid argument. I say, you know why you couldn't figure that out? Because the topic distracted you. You have strongly held biases and opinions that clouded your judgment on whether or not this argument made sense. And that's where the mind control comes in, because that's what advertisers and politicians and the media do all the time. They tug at your heartstrings so you can't figure out that what they're saying makes no sense at all. So what do I then tell them? We're going to go past that in logic, because we're going to study whether an argument makes sense without even knowing what the topic is. Because it's hard to decide if something makes sense when you're biased by your emotions involved in a topic. And so that's what I will tell them, and that's what we're going to do here. So when you're sitting there going, P implies Q, that's stupid, it doesn't mean anything, I can say, yes, it does. P is a real statement. I just don't want you to know what it is, because now you can think about whether the argument makes sense without your personal biases. They like that one. Graphing, math and the economy. Here's how we teach graphing. That's how they teach it in high school, grade school, wherever it is now, I don't know. And then we recover graphing in beginning algebra and intermediate algebra. This is the way most people teach it. Plot a bunch of points, connect the dots. Why? Because it's the best way? No. Because it's easy. Anybody can do that. Anybody can plot points and play connect the dots. Hell, kids did that when they were like 2. The only difference is, instead of getting like a dancing banana, you get a parabola. And then we wonder why students don't understand what graphs are for. They think it's bad art. And it's our fault, because we taught them that it's bad art. We taught them, what do you do to graph? Oh, you plot points and you play connect the dots. It's completely the wrong way to start, and it's a perfect example of the value of teaching backwards. I did this example in both a beginning algebra course last semester on the first day, and, well, maybe it wasn't on the first day, that's a lie. Bad boy. And on the first day of a Calc 1 class this semester. You can't see that at the top of the screen. It says U.S. unemployment rate by year. So here's a table of actual data that gives the unemployment rate per year. And the question is, to the students then, describe the unemployment rate, the trends over this 20-year span. So when you've got data in a table, what do? You look at it and go, okay, 7.5, 6.9, okay, it went down, 6.1, it went down again, 5.6, it went down again, but not as much, 5.4, it went down a little bit, 4.9, it went down more, and by the time you get to 2010, you've completely forgotten what was happening in 1992, because there's just too much data there to study one piece of information at a time. So instead of having students look through this table one piece at a time, what if I graph the data? Two things become immediately apparent. Number one, the graph looks a hell of a lot like the Lake Cumberland sea monster, which doesn't exist. It's totally irrelevant, but pretty cool. Number two, more importantly, it makes it completely obvious what the trends are. You don't have to be an expert in mathematics. You don't have to be able to find the domain of a function to look at that and say, oh, looky there. Unemployment went down pretty steadily from 92 to 2000, and then that went back up and so forth. First example I do in graphing in every course where I recover graphing, because I want them to look at this and say, that's the point of graphs. It's not about plotting points and connecting the dots. Nobody cares. But a graph is not something you should be afraid of. It's not something you should avoid, because it's better than an equation, and it's better than data. If you want actual specific information, of course the table and the equation are fantastic. But how often do we need exact specific information? More often when we're evaluating something, we want to know overall picture of what's happening. That's what graphing is about. Topic, approximate integration. I don't want to leave out calc stuff. I call this math and childlike wonderment. It says a lot about the way I view the world. 2 falls ago, my wife and I were hiking at Salt Fork State Park, which is a wonderful state park in southeastern Ohio. It's actually my favorite place in the state of Ohio. And it's in this really weird geologic area at the sort of foothills of the Appalachians, where you're walking through the woods and all of a sudden there's just this big rock sticking out of the ground for no reason whatsoever. And I love stuff like that. I thought it was so cool. So I had my lovely wife, posing next to the rock, and I have a whole bunch of different pictures from different angles, and there's some with me in there. So she hates when I show that picture because she was like, wearing sweats and hadn't showered or anything. Sorry, honey. So here's what she looks like in real life, to be fair. So anyhow, as we're walking along after taking pictures of this rock, because I view the world in a sort of goofy, childlike way, I thought, I wonder how much that rock weighs. How strong would you have to be to lift that thing? Could Superman do it? And it occurred to me later, it's not an untenable problem, because I have pictures from different angles. I know how tall my wife is. She's right there, as a matter of fact. So I can get measurements using that scale from different angles of this rock. I could then possibly use Simpson's rule to figure out cross-sectional areas, turn that into potential volumes. I could get online and do some research and find what the density of this type of rock is that sticks out of the ground at Salt Fork State Park. I haven't assigned this as a Calc 2 problem yet because I haven't gotten my fingers around all the edges of the details, but I'm going to someday. And I looked at it and said, hey, there's a really cool math problem. I don't know exactly how it's going to work out, but I know I'm going to do something with it. And I really love doing stuff like that. Now, the eternal question. Why are we here? Isn't that the eternal question? Or, as we say in math class, why do I need to know this? Now, when students say this, here's what we really hear. I used to, like all young teachers, I used to avoid this question like the plague. I would do anything to have students not ask that question, because I didn't have really good answers. I would just say, because it's good for you, it makes you smarter, which is true. I mean, any class, a student is exercising their mind and improving their problem-solving ability. All of a sudden, it occurred to me, there's the answer, exercise. So I came up with this analogy. I'm fond of answering questions with questions. So for a while, I would wait for students to ask this question. I would spring this on, and then I got to the point where I asked it for them. Student says, hey, why do we have to do this? This is stupid. I'm not going to use this in my job. Oops, I went the wrong direction, didn't I? So one of my answers to them is, it's the wrong question. The question isn't, why do I need to know this? You don't need to know anything. You can stay in your parents' basement for the rest of your life and not do anything. Stay protected in their warm little cocoon. You don't need to know anything. The question is, why is it useful to know this? So when students say, why do I need to know this? I'm not going to use this in my job. I'll say, let me ask you a question. You exercise? You run? Every student's going to say yes, whether they do or not, right? Because nobody wants to sound like they don't exercise. So I'll say, all right, why do you do that? Well, that's stupid. Well, you can use that in your job? What are you, bank robber, track star, run away from the police? Huh? Think about how stupid running is. I'll do an actual physical demonstration here. Okay, I'm going to run out of the camera screen again. Sorry. Okay, I start here. I'm not a runner, you can tell. I expend a whole lot of energy. Net result? Nothing. I ended up exactly back where I started. I accomplished nothing for all my effort. And students will laugh and say, oh, well, that's stupid, because of the exercise. Why do you get that? Why is it so easy for students to understand the value of exercising this part of the body, and then we try to give them this great opportunity to exercise their brain, and they just reject it, say, this is stupid. I don't need to do this. I don't need to know this for my job. It's a fantastic way to convince them that even if you don't like math, at least respect it. That's one of my catchphrases. I say, I don't care if you like this class, at least learn to respect the value of challenging yourself and exercising your mind and becoming a smarter person. And when they complain and say, oh, I don't like this because it's hard, well, you could go to the gym and pick up a little 1-pound weight and go like this for an hour. And then go, oh man, I'm all pumped up and stuff. But it didn't do you any good because it was too easy. It's great that math and science classes are hard. That's what makes them useful. If it was easy to get a college degree, everybody would do it, and your college degree wouldn't be worth any more than your high school diploma was. I try like crazy, and I fail as often as not, but I try like crazy to get them to understand that's what's good about math classes, an ability to exercise their mind and make them smarter and more attractive. Because let's face it, here's one of my favorite analogies, I'll say, no college girl has ever sat next to a guy in class and said, you know, he's kind of cute, and I saw him in the parking lot, he's got a nice car, but he's just not dumb enough for me. We have to let them know that, and when you become an adult, smart is a good thing. It makes you more attractive as a friend, as an employee, as a mate. Teach them to strive for being smarter and exercise their brain. Another question. Oh man. That says, can a test be, gasp, fun? The answer is no, because the only thing that stinks more than taking a math test is grading a math test. A more relevant question might be, can a test suck less? And my fellow Americans, I say yes, it can. Want students to relax on tests? Lighten them up. Put some fun stuff on there. Give them a little chuckle. If you're not funny, ask one of your funny friends to put some stuff on your test. So this is one of the things that boy, that went over well. I'm kind of locally famous at my campus for being the guy that puts goofy stuff on tests, like, funny instructions. I'm not above threatening them. I actually got in trouble last year because I handed out a version of this where it said, then get the hell out of my classroom. And someone went and complained to my superior. Not just instructions, though. I'm locally famous for ridiculous, goofy word problems. I have word problems about math professors stranded on desert islands with supermodels and casks of rum and so forth. So there's one of my classics. Oh, I love this one. Right? Isn't that great? Isn't that what they say when they get a tattoo? I want to express my individuality. So the content of these is not important. All I'm saying is, just if you do something to lighten up the mood a little bit, it'll help the students, they'll appreciate it, they'll relax a little bit more. And I mentioned ulterior motives before. My ulterior motive in problems like this, I think they're really valuable, as goofy as they are, because a thing that stinks about all the word, not all, but most of the word problems you see in books, they give the student exactly the information they need and nothing more. There's not a word in there that doesn't have to be there. Life does not work like that. I'm sorry, folks. When there's a problem to solve, the world doesn't just drop a bunch of tools in front of you and say, here's what you have to work with. I think there's a lot of value in being able to sift through all of my crap to find the useful information in the problem that they need to solve the problem. And so I give them a lot of problems to practice like this, and I put them on tests, and I know it makes an impact, which I'll tell you about in a second. I'm also sort of locally famous for doing this as extra credit questions on tests. Now, some people would say, oh, that's not fair. You're giving credit for non-mathematical stuff, but most students get a point twice a semester. It's not that big a deal, but they look forward to this. Once in a while, I'll leave off the cartoon and put some trivia questions, and they complain. Hey, Dr. S, where's the cartoon? And it makes it more interesting for me to grade the test, because as I'm suffering through the wrong answers and writing corrections, I know at least when I'm done, there's going to be a couple of funny captions to brighten my day a little bit. So the story that I like to tell about this, I guess it's been about 6-7 years ago now. A student pokes her head in my office. I recognize the last name of a particular student. Her name is Stacy Ellison. And I recognize the last name. Of course, it's not uncommon to get siblings of former students. And I remember a guy named Kurt. So about the second day, she pokes her head in my office after class. She says, hi, Dr. S, I'm Stacy Ellison. And I say, yeah, I know. And I say, how are you doing, Stacy? What can I do for you? She says, well, I just wanted to say thank you. I said, okay, you're welcome. What did I do? She said, you had my brother Kurt a few years ago. I said, yeah, I remember. I noticed your name kind of jumped out at me. She said, well, when he was taking your class, I was in the service and I was stationed in Iraq. And it wasn't a real great area and there's a lot of bad stuff going on. You really learned to look forward to calls and messages and mail and stuff from home. And Kurt used to make copies of his tests because he thought they were so funny, and he'd mail them over to me. And then I'd share them with the other people in my unit, and it was just really nice. It was like a little break from the war. We look forward to getting these tests. And I get chills every time I tell the story. Can you imagine that? Something as ridiculous as writing a story making fun of kids getting tattoos on a test had that sort of impact 6,000 miles away, it really makes you think we're in the right profession. We're doing this for the right reasons, because even if it's not finding X, there's a lot of stuff we do that makes an impact on a lot of people, so go USA. In summary, have fun. It's fun to teach this way. It's fun to live this way. It's fun to go on a trip and look around and see, hey, there's a math problem that I can write when I get home. It really is a lot of fun. Be inspired and be inspiring. Don't be inspired by me. It's not what I'm here for. Be inspired by your life. Be inspired by the world around you. Look for examples of things that you can use to make math and make your teaching come alive, and in turn, you will be inspiring to your students. Not all of them. Some of them are going to tune you out, but there's going to be that stray kid who tells you about what happened in Iraq that made a difference in her life. There's going to be the student who uses math to figure out a way to stockpile thousands of dollars of cash under his mattress that his parents don't know about. Show your students how math is used in your world, and if all else fails, distract them with a picture of a monkey riding a dog. Thank you for encouraging my questionable behavior. If you have any comments, questions, suggestions, or dirty jokes, I would love dearly to hear from each of you. Here's my contact information. Thank you all for being here this evening.
As a gift for coming
my
and talking
gosh.
to us, we decided to come up with a bunch of things that represented different parts of the state of Kentucky.
Sweet.
We got things from Owensboro that our past president promised if there was any bourbon balls missing, she did not eat them. And we've got the Louisville Slugger. You might be able to use this on the students who ask him bad questions.
Let's see how they... Yes, that will work nicely.
Just right.
Oh, that is awesome.
And some local literature. I know you're into literature. And we also have an apron to go with the cookbook.
Love ghost stories. Awesome. Thank you so much, Don. That is awesome. That's great.
That's